So today we have a guest lecture I'm super excited about. We have Professor Somil Bansal, who's in the AA department here. He leads the Safe and Intelligent Autonomy Lab. And before that, he was an assistant professor in electrical and computer engineering at USC. And before that, he was a research scientist at Waymo. So super excited to hear your lecture.
Thank you. Hello, everyone. I'm Somil. First of all, thank you so much, Mykel and Sydney, for offering this wonderful course. Several of my students are taking this course, and they absolutely rave about this. So in my spring break, I'm planning on catching up on the lecture videos, which I have access to. So I'm very excited to be here and talking about some of the work our group has been doing on mining failures in vision-based controllers, which I think is quite related to some of the topics covered in this class. So at a high level, sort of our group focuses on robotics and autonomy, with the general goal being developing robot algorithms that operate with guaranteed safety and performance in new and uncertain environments. And we focus on developing these algorithms in the context of a variety of different applications, ranging from autonomous drones, autonomous cars, aircrafts, and space robotics. In a lot of these systems, machine learning is becoming increasingly pervasive in their autonomy stacks. The predominant one still remains perception and vision, but now also in prediction and behavior forecasting, and then planning and control as well. And for a number of good reasons, machine learning is really good at capturing the complexity of real-world situations these systems must operate in, which could otherwise be very hard to model using engineering domain knowledge. But not without some pitfalls. So incorporating of machine learning has also opened up a set of new safety challenges. And you know, the one very close to my heart is this rollback of cruise cars from the San Francisco city. And since then, actually, they have terminated their operations altogether in autonomous driving. The issues were severe enough that the US government, now almost 1.5 years back, but also a couple of other governments, notably UK government, passed this executive order to prioritize discussion on AI safety, both for autonomy, but sort of AI more broadly. And so coming back to autonomy, there is this tension that we have a lot in autonomous systems today, which is how can we leverage the capabilities offered by modern machine learning methods while also maintaining safety? And so that's really is the core focus of our lab these days. And our approach to sort of overcoming this challenge is to think of safety of AI-based systems more as a continuous process, where safety is integrated in different stages of this data cycle or the system cycle, starting from the training time to the deployment of the systems and iteratively improving the safety over the system's life cycle. And so that's a mouthful. What that means really is we think of safety in 3 different stages. We start from the training time and we ask ourselves, how can we programmatically incorporate safety requirements in the training phase itself so that we get safety-aware policies or safety-aware AI systems as a result. And so one way to think about this is we are asking questions of how to ensure safety within the training data distribution. But that is not sufficient when we deploy these systems in new and uncertain conditions. So we have to ask ourselves, you know, when are we going out of distribution? And how can we adapt our safety corresponding to these out of distribution scenarios? And finally, we focus on developing methods that allow for stress testing of these systems to mine their safety critical failures and use them to improve the design of the system, so thereby closing this loop. And so together, this framework allows for a continual safety assurances for learning-based systems where safety is provided provisionally during the training time, they are adapted during the operation time, and they are improved over the system's lifecycle. But for the remaining time that I have today, I want to focus on this last component, and in particular, the stress testing component, which is how can we stress test a learning-based controller to mine its safety-critical failures, and then I will talk about how can we use those failures to improve the system itself. And we have been particularly asking this question in the context of vision-based controllers for two reasons. One, vision-based controllers are becoming quite ubiquitous now in the autonomy stacks, but also traditionally stress testing these controllers have been very challenging for control theoretic tools because of the high dimensionality of vision-based controllers and also their complicated input spaces like RGB images. So let's talk about how can we stress test these systems or these vision-based controllers. So let me first formulate the problem mathematically. So we are given a system which has, so this could be a robot which has some dynamics with state X and control U. Now at each state, we have a visual sensor that gives me some visual observations. So these could be RGB images or point clouds, which are then taken as input by the vision-based controller, and that gives me the control to be applied on the robot. So this forms a closed loop system. And we also assume access to a simulator that we can use for stress testing this control. And so our goal here is to find these safety critical failures, in other words, find the visual inputs I that leads to the safety of the overall, or that leads to the violation of safety of the overall system. And really, the approach we take here is to cast this failure discovery as a reachability problem. And so the way to do that is essentially we can concatenate the visual observation function along with the vision-based controller to obtain an equivalent state-based policy for the robot. And so I can simplify for the stress testing purposes my closed loop system as the robot in closed loop with this equivalent state-based policy. And on this particular closed loop system, we can use a lot of existing reachability-based methods that at the end of the day compute what we call backward reachable tube or some version of backward reachable tube, which at least in English means that the set of all initial states of the system which will eventually steer the system into some predefined failure region under this controller, in our case, this controller G. So what I want to do is I want to talk a little bit about what this backward reachable tube is and how can we compute this backward reachable tube, and then I'm going to come back to this problem and talk about how that backward reachable tube could be useful to find the safety critical failures that I'm after. So let me give a 5-minute primer of Hamilton-Jacobi reachability, which is one of the reachability methods to compute this backward reachable tube. So in reachability analysis, we start with the dynamics of the underlying system, which we assume has some state X, control U, and disturbance D. Disturbance here could represent the modeling uncertainty in the system. So for example, we might not have fully modeled the system, or could be some external disturbances that we may want to safeguard against. Now, given these dynamics, once again, the key thing we are interested in is the backward reachable tube of the system, which is the set of all initial states from which it will be ultimately driven to an undesirable set of states, sometimes also referred to as failure set, despite the best control effort. Pictorially, what that means is, let's consider a very simple example. Imagine there's a quad rotor flying longitudinally in this room. So in this particular case, ceiling and floor might be that failure set that we don't want the quad rotor to crash into. And this light red region over here is the backward reachable tube, meaning that if the quad rotor starts inside this set, then no matter what it does, it will eventually crash into ceiling or the floor, or in other words, it will eventually enter the failure set. The converse of this backward reachable tube is this blue region or the safe set, and reachability analysis provides the guarantee that if the system starts inside this set, then there exists a policy to keep it inside this set at all times. In other words, this blue set is control invariant set. And the way we compute this blue set and the corresponding safety controller is by converting this whole safety problem into an optimal control problem, which can then be solved using a variety of optimal control methods. And the first step to do so is to implicitly represent our failure set, such that this function which we are using to implicitly represent the failure set is negative inside the failure set and positive outside. So in this particular case, it should be negative inside the ceiling and the floor and positive everywhere else. And the intuitive way to think about this function L is the safety reward the system get at state X. So if you are inside the failure set, you get a negative reward, and if you are outside the failure set, you get a positive reward. And there are many such reward functions one can use. In fact, any reward function that satisfies this property is good enough. So we only care about the sign of it. And a popular reward function is the sign distance function to the failure region. Now, given that reward function, the cumulative reward or cost of a trajectory is given by the minimum safety reward incurred along the trajectory. So the reason to define such a reward function is that if the trajectory ever enters the failure set, this cumulative reward will be negative. Otherwise, this cumulative reward will be positive. So by just looking at the sign of this cumulative reward, I'm able to tell whether the robot trajectory has been safe or unsafe. Now, of course, I can pick my control so as to maximize this reward, in other words, to keep the system safe. So what we are after is really this game where the disturbance or the uncertainty is attempting to force me inside the failure region. In other words, it tries to minimize this cumulative safety reward, and the control is trying to keep me safe. In other words, try to maximize this cumulative reward. In other words, we are interested in the value function corresponding to this cumulative reward function. And value function here intuitively represents the closest the system will ever get to the failure set. So if the value function is negative, that means despite my best control effort, my trajectory must have entered into the failure region at some point. And hence the states where the value function is negative are the unsafe states for the system. And the converse is the case when the value function is positive. That means the trajectory of the robot remained outside the failure region. And so this optimal control problem, once we solve this and obtain the value function, it gives us a simple characterization of the unsafe set, or the backward reachable tube, which is the backward reachable tube is same as the states where the value function is negative. Now, to obtain the value function, we can use a variety of different optimal control methods ranging from MPC, dynamic programming. The one that's quite popular for assurance regions is the dynamic programming because it provides us the globally optimal solution to this value function. And that results into a Bellman backup or a Bellman iteration, just like value iteration. But when we are operating in continuous state and time, that Bellman backup is given by a partial differential equation. It's just a continuous time version of the Bellman equation. But it does exactly what Bellman equation does. It tries to measure the change in the value function upon taking a particular action U. And if we solve this partial differential equation, we get the value function. Here I'm showing the value function for that quadrotor example. So the red meaning, or the darker red meaning the value function is more negative. The darker blue means the value function is more positive. So in this particular case, intuitively, the value function is maximum in the middle of the room, which makes sense because I'm further from the ceiling or the floor. So I'm farthest from the failure region. Whereas if I go towards the failure region, it starts becoming red. Now, one quick question is the value function is more red here, but not so much on the top, even though the failure set is symmetric. It's ceiling and the floor. Why do you think this disparity in the value function?
The control authority, because it takes more control authority near the bottom to save the drone from crashing than it does near the top.
And why is that?
I guess it probably has to do with the dynamics of the drone.
Yes, that's exactly right. It's because of gravity. Because of the gravity, by default, the robot is being pushed towards the downside. So with the same control effort, the value function is going to be more negative towards the bottom as compared to the top. So again, in this particular case, this is a simple example. We don't really need to go through the trouble of solving this partial differential equation to come up with the unsafe set. But the point of this example is, A, this method is quite general, and B, it captures these effects in the dynamics that could be otherwise very hard to reason about automatically in the value function computation. Now, along with this value function, which tells me about the safety, it also gives me a safety controller, so keep me within this blue region. And intuitively what this equation is saying is that at any state x, this controller is trying to do gradient ascent in the value function. In other words, it's trying to push me towards more and more positive values of the value function, because the higher values or higher positive values means I'm more safe. Okay. Before I continue, a shameless plug. I'm offering a course where I cover all of this in much more detail in the spring quarter. So where we will discuss different ways to compute backward reachable tube and safe sets using techniques like artificial potential fields, control barrier functions, and Hamilton-Jacobi reachability that I just presented. It's a graduate level course with the focus more on the course project and a couple of homeworks. Okay, let's go back to the core problem at hand, which is how can we mine the safety critical failures of vision-based controllers. And just to recap, I was saying that we can combine the robot observation function along with the controller to obtain an equivalent state-based policy for the robot. So my closed loop system can be simplified as follows. And then for this system, I can compute the backward reachable tube, which is the set of all states from which the system will eventually steer into the failure region, despite the best control effort, which now we know is equivalent to solving this partial differential equation that we saw earlier. Except that here, I'm not looking for best control action. I'm already given a controller, this learning-based controller over here. So I can just do small substitution, which is the set of states which would fail under this controller g of x, which is same as, rather than optimizing the controller, we will just plug in a specific controller. So we still need to solve a partial differential equation, but a simplified one. And if we do that, then we can get the backward reachable tube. And here is one example. I will go through this case study in much more detail, but once we can compute this backward reachable tube, we might get this region, for example, this red region, which indicates the set of all initial states that's going to eventually fail. So we can look at the images seen by the robot along these states and get the failure images. So that will be the strategy. So we start with a vision-based controller, convert it into a state-based reachability problem, we solve that reachability problem, and then go back to the vision or the RGB image space by looking at those failure states. Any question on this strategy before I move forward?
Does this account for the fact that one stage is not to multiple different images?
That's a very good point. So the images are a function of course, the state, but other environment parameters. So for example, the same image would be different if you are in the daytime or in the nighttime. So I will, to some extent, we can account for it, but environment variations are still very hard to handle here, and that's one of the things I want to discuss later. Okay, I'm gonna skip a couple of slides. So let's apply this framework in the context of an autonomous aircraft taxiing problem. So here, this aircraft is using a vision-based controller that uses the camera images from the right wing of the aircraft to keep this aircraft on this runway, or taxi the aircraft on the runway. But in the process of doing so, we don't want this aircraft to steer off the runway, which in this case represents the failure set over here. Now, using the method described that we just discussed, we computed the backward reachable tube of the system. And so the red region here represents the set of all initial conditions of the aircraft from which it will be driven off the runway under this vision-based controller. Similarly, the blue region represents the set of all initial states of the aircraft from which it will remain on the runway at all times under this vision-based controller. And here are some of the images robot sees along this failure region. So these are essentially our set of failure images that I was after earlier. Now let's take one of this failure image and let's see what's going on. So this is just a bigger view of the same image. So this is the first person view, which the controller sees to make the decision. And the top view here is just for reference. And based on our analysis, we expect that from this condition, the aircraft will steer off the runway, as it is happening here. But what was interesting is why the aircraft failing in this particular initial state. And upon the analysis, we figured out it is because of these markings on the runway. The CNN here was confusing these runway markings with the center line of the runway, and it was steering the aircraft towards it. But by the time it's realizing that it's actually not the runway center line, it is already too late and the system steers off the runway. So by doing this reachability analysis, we can find such semantic failures of these vision-based controllers. Now what I want to highlight, which is very important, is that these are not just any vision failures. These are the vision failures that then lead to the system failure as well. So to highlight that difference, here on the left, I have the backward reachable tube, which is kind of an indicator of the system failure. So the red means system fails and the blue means it does not. On the right here is I'm plotting the prediction error of this vision-based controller. So the red means a high prediction error and the blue means a low prediction error. Now what's interesting is that there is a whole bunch of states where the prediction error is really high, like on the top there, but that has absolutely no effect on the system's safety. So the vision can make a high error, but that's compensated downstream by my planner. And hence that does not lead to the system failure. On the other hand, there are some states where the prediction error is really low, but that is sufficient to trigger the system failure. And so what this is indicating is that not all perception errors are equal. Some of these learning errors can matter much more for system level safety. And here, when we are developing this BRT-based framework, we are targeting those failures of the vision component, then that lead to system level failure. So it's going to be very different than if you were to do a component level analysis of the same vision-based controller.
So with this reachability analysis, we find the set of initial states that lead to failure. There are images that we capture along the trajectory that we spawn over the course of the trajectory. So do we actually have a way to know which of those images, I guess, are more important for why we result in failure?
Yeah, that's a good question, and something that I have thought a lot about myself too, which is which image I should assign the blame of failure to. The short answer is that I do not have right now a way to assign the failure. Even if you tell me the image which is actually corresponding to the failure, I don't know what is the visual feature in that image that's causing the failure. So that's actually one of the limitations of this whole pipeline, which is it tells me the set of failure images, but doesn't give me any underlying reason for that failure. So this analysis that we did, where I said this is the center line of the aircraft, or this runway marking is what's causing the failure, we had to do a lot of analysis, blocking in different parts of the images to figure out what in this image is actually throwing the CNN off. So it's a very hard analysis to do. In fact, even in the state space, that's a very hard analysis to do. So given a failure state, it's hard to tell which part of the state is precisely causing the failure.
I think I missed a little bit what type of vision models we're considering here. You mentioned a CNN, but can you have like really large, let's say a ResNet or something like that, or vision transformer?
Yes, in fact, the next case study is going to use a ResNet case study. To answer your question in short, here I'm treating the entire vision-based control as a black box. So it could be anything. It doesn't even have to be a neural network based yet. So it's a black box analysis in that sense. Earlier somebody asked me what happens across variations in the or visual variations. So we can also compute this backward reachability as a function of different environment latents. So for example, here I'm showing the BRT, the same BRT corresponding to different times of the day here. And what's interesting is that maybe a little bit less interesting part is that the BRT overall grows when you go from day to night, which we expect for a vision-based controller because visibility is lower in the night. But what's particularly interesting is the state that was causing a failure earlier because of these runway markings is actually not a failure state in the night. It's actually in the safe region. It's in the white region. And that was very counterintuitive at first, but then if we think deeply about it, the state was causing a failure because of this runway marking. And in the night when those runway markings are not as clearly visible, the CNN is not thrown away by that, and hence it remains safe during the night at the same state. Mykel.
Maybe just a question on the previous slide, which I think is related to this. How did you make the plot on the right?
So here I'm using the full privileged information about each state. So what I'm doing is I'm going each state by state. I'm looking at the image corresponding to that state.
So you teleport the aircraft with that particular heading angle, and then you measure the prediction error by the offset.
Exactly.
Okay.
So because I'm in this sim, I have the privileged access to what it should be predicting, and I can see what it is actually predicting, and then I'm computing that error.
Got it. But that would be for one particular time of day.
Yes, that is for the night. Yeah. So here we are looking at the variations across time of the day. We can do also variations across cloud conditions. So this is what the value of that state looks like across cloud conditions. And by doing this analysis across different environment latents, we can collect a set of failure images across a bunch of environment conditions. Now here we are applying the same framework to a different vision-based controller. So this is for indoor navigation. Here this robot is using an RGB image from the onboard camera and using a ResNet architecture to convert it to a waypoint to go to, which is then tracked using a low-level MPC controller. So my entire vision-based controller here is going from this image to some control to be applied on the robot. But internally it has a bunch of different submodules. And a little bit of context about this vision-based controller. This was trained entirely in simulation using photorealistic simulators, where most of the data was actually collected in Stanford buildings. And this controller leads to pretty good sim-to-real transfer. Here is one experiment that was done in Berkeley, so clearly was not seen during the training data. This is only what robot has access to. These are just for the context. And it leads to pretty good sim-to-real transfer overall, where it's going through very cluttered hallways based on this monocular RGB image and reaching its goal in the end. But once again, we use this vision-based controller and pass it through our stress test pipeline, and we encounter a number of interesting failures. I just want to highlight one that I thought was puzzling me for a long time until we did a lot of analysis on it, is that this CNN actually learns a correlation between light-colored walls and traversability, or light-colored surfaces and traversability. And the reason for that is this controller was trained entirely in sim, and in sim, all the data that we had light-colored floors and dark-colored walls. So it learned this spurious correlation that whenever you see a light-colored surface, you can go through it. So during the test time, when we did the opposite, where you have light-colored walls and dark-colored surfaces or floors, it thinks that it can go through the wall and collides in the end. So there are these type of spurious correlation that CNN learned, and we can expose that through this stress testing mechanism. Okay, so where am I going with this? Well, we now have a set of failure inputs for these vision-based controllers. So we can use them to improve our controller itself. The one thing we can do is we can use these for a runtime anomaly detector. So we can simply train an anomaly detector that, given an image, predicts whether this image is likely to cause a failure or not. And this anomaly detector then can be used to trigger a fallback controller in case a failure is predicted to safeguard the system. Otherwise, we can just keep running our vision-based controller as it is. Yes?
So how is the anomaly detector implemented? Like, what are you giving it, what actually happens, and how is it making the prediction?
Yes. So I'm going to show an example soon, but essentially the failure, so we got this bunch of images which we know are going to cause a failure in the system. Similarly, we go in the safe region and do the same process, and we're going to get a set of safe images. So essentially, it's simply a binary classifier, which gives me either a failure or success depending on the image.
So it seems like, you just have like a neural network here. So it seems like the anomaly detector doesn't have to be like 100% deterministic. Why is that the case?
It doesn't have to be, it is still deterministic at the end of the day because we're going to put some threshold on the failure and success detection. It is not 100% correct for sure, if that's what you meant.
Yes.
So it is only likely to work in in distribution. In other words, whatever environments you use for stress testing, you got failure images within that. And so if you're going to encounter the images from the same distribution, then this anomaly detector is going to work, otherwise it does not. So far, in general, I haven't commented anything about what happens out of distribution. So out of distribution of the environment, out of distribution of the visual variations. And I'm going to talk about that in a little bit. So here is that anomaly detector in action. So this is the same image, if you recall, where the vision-based controller was earlier failing because of these runway markings over there. But now you will see that as soon as the aircraft sees this image, anomaly detector flags that as the failure image. Fallback controller triggers, which in this case simply slows down the aircraft. So it's a very simple fallback controller. And once the aircraft passes these markings, then the vision-based controller takes over again because anomaly detector classifies it as safe. So this is a simple mechanism for runtime anomaly detection that we can use once we have the failure data set. We can also use this failure data set for the incremental training or targeted incremental training of our vision-based controller. So we collected a bunch of images and the labels corresponding to those, and then we just did more training iterations of our vision-based controller. In the gray is the backward reachability before retraining, and the blue is after retraining. So as we probably would expect in this case, the BRT gets smaller when we retrain because now the vision-based controller knows how to act under these failure scenarios.
Did you compare this with what would happen if you had full observability? Because I think there's still some mistakes you just can't recover from.
Yeah. So there actually I'm going to show you some more slices of what happens with incremental training, and the issues are much deeper. But to answer your question, in short, yes. So after retraining, the vision-based controller still has some failure modes. But two, if we use a perfect controller, so imagine the vision-based controller was perfect, just because of the choice of our controller, we may still have some failures say that we cannot avoid. And here, the blue side is quite close to that. I mean, we did that analysis, but I'm not showing it over here. So let me quickly summarize this part. So we have been talking about stress testing vision-based controllers, and what maybe my 2 cents here are is that data-driven reachability methods can help with the efficient stress testing of vision-based controllers. And these mine failures can be used for closing the loop both with offline design, for example, this targeted retraining, or with online deployment, for example, via anomaly detection. So that could be quite useful for real-world systems. Now, I want to talk about some of the challenges which already came up when we were going through the framework. One is I can only hope to safeguard against the environments that I have seen in my stress testing or during my stress testing. So, for example, I never talked about the runways with snow or ice on them. So if such a runway is, if the aircraft is operating on such a runway, I have no hope that the anomaly detector would work. So it's an open question so far, for at least for this work, is how to generalize to new environments. Now, there could be a few methods to tackle that, which we've been thinking about. For example, we can do digital twins. So as we go to the new environment, we can try to create a twin of that in simulation and then use it for stress testing, just like we've been doing for other environments. The other interesting idea could be vision models. So we have nerves and Gaussian splatting models now, which can generate rich visual models with a few images. So you could imagine that as we go to the new environment, we can create these visual models and use them for stress testing. So we have a good sense of the failure scenarios within a particular environment. So if this stress testing pipeline can be run efficiently enough or quickly enough in an online manner, then we can deploy them to new settings. Second, and something very interesting to me, is when we do this incremental training, which by the way is very common across industry as well. So, am I being recorded? I'm being recorded, right? Okay. So I'm just going to keep it industry generic. So if we look at different autonomy pipelines, and many companies keep track of what are all the failure modes of their pipeline is. I mean, they don't necessarily always do stress testing in the way I'm proposing here. So the stress testing can be done with an infill testing, for example. Maybe like there is an actual human that is operating the autonomous system and taking a look at where it fails. So essentially, we might have a catalog of failures. But using that catalog of failures for improving the system is a huge challenge, because there's an underlying issue in our machine learning systems today, which is we don't know how to lead to monotonic improvement in our neural networks. So if I give you data set D1 and I add 100 more data points to D1 and I give you a new data set D2, there's absolutely no guarantee that D2 will actually lead to a better performance of this neural network compared to D1. So there is no rule for monotonic improvement in our neural network. And those cracks are also apparent here. So it is the same BRT before retraining, which is in the gray, and after retraining, which is whatever this color is, light brown. I showed you one slice earlier. Here is another slice of the same BRT. And you can see that actually now the system is failing in the situations where it was fine earlier. So this is what I'm talking about, where we trained it on more data, more targeted data, yet the safety might actually took a downturn in some of these situations. And the another big challenge here really is how to identify the underlying failure reasons. So currently, the framework only gives me these images. Only tells me that these images, starting from these images, the robot is going to fail. But what is in this image that's causing this failure is very, very hard to tell. So for that, we are doing manual analysis for now. So, I guess more my students and myself are just looking at these images and trying to come up with the reasons for why it might be failing. Maybe with the foundation models that might change, but still finding the underlying reasons concretely is a very, very big challenge. So whatever I told you regarding pedestrian crossings, it should not be pedestrian crossing, I was told, runway markings, or narrow gaps or wide walls, the reason it was causing the failure is all manual analysis so far. And part of the reason for why we have to do this manual analysis is also because of the choice of the framework I'm using. So I'm treating this entire vision-based controller as a black box. And yes, that allows to do a slightly simpler stress testing analysis. The issue comes up at the interpretability level. So given a failure image, this black box mechanism makes it very challenging to assign the blame on any particular module of the entire pipeline. On the other hand, if we look at most of the autonomous systems today, and here I'm taking autonomous driving as an example, we have a modular pipeline. We have perception components, which then feeds into, for example, prediction component, which then feeds into planning component. And so an interesting question to ask here is, what is the difference between this sort of black box end-to-end stress testing versus modular stress testing and anomaly detection? And can it help in any way with the interpretability? In particular, we have years of research on each of these components individually. So for example, today we have very good perception monitors, which can rely on sensor fusion, for example, LiDAR, radars, and cameras in the case of an autonomous vehicle, and tells me if a particular scene might have a perception error. That's all it's able to tell. Not necessarily the failure of the entire pipeline, but just whether there is an error in the perception component. But as we talked about in the aircraft example, not all component level errors are equal. So let me rephrase that in the context of this autonomous driving example. So imagine we have this green car is our autonomous car. Both the yellow and the red cars are the other agents. And suppose I come up with this blue plan to turn around. Now imagine my perception component here fails to detect both of these red cars. Now if it fails to detect red car 1, it does not affect the safety of my plan whatsoever. My plan would not change at all whether or not I detect the red car 1. I'm not saying that the modern perception component would not be able to detect red car 1, just to be clear. I'm just taking it as a cartoon example. On the other hand, if it fails to detect the red car 2, that has a clear effect on my safety. And so when we are looking at these modular pipelines, an equally important question to ask is, which of the perception errors, how does a perception error affect the overall safety or the system level safety of my system? And so we have been studying this problem in collaboration with NVIDIA in the context of autonomous cars, where we have been looking at coming up with ways to evaluate the system level safety given a perception failure. So we are starting with a perception monitor, which takes a scene or row sensory inputs, and it tells me what we call monitor input. So it tells me if it has missed some of the cars, and if so, where. So it's essentially a probability distribution of some of the missed agent positions. That's what it is in this particular case. And what we do is we design this neural network, which we call Spark, which takes that monitor input along with an ego plan and the scene, and tries to do a safety assessment of that plan, meaning it tries to tell me whether that particular plan can be unsafe under this particular perception error. And if it is leading to an error, it also suggests a repair or how to change that plan so as to maintain safety. So, yes?
Sorry, this is something at runtime or at like...
Yes, this is runtime. I'm going to train this network offline, but the hope is to run it online.
Okay,
and sorry, go ahead.
I kind of didn't understand. You said that we can like put in an input but leave out some of the cars or whatever, and so at the very input.
Yeah.
This is running at runtime. So we put in the runtime input, but then we might have missed a car. In the scene.
So there is perception monitor, which is more like a sensor fusion in this case, that taking in all the inputs and telling me if there is a probability of misprediction of some of the cars.
Okay.
So
it's like predictive uncertainty kind of.
Exactly.
Okay.
And there could be different type of predictive uncertainty. Okay. It could be about speed of the car, or it could be about misdetection. In particular case here, I'm looking at misdetection, which is, this is essentially going to tell me about the position of some uncertain agent, for example, or a distribution of that, which I'm trying to figure out if going to affect my safety or not. And the whole problem really here is runtime. The issue is that the latency requirements of these autonomous cars is very, very low. So we can, indeed, we don't even need a neural network. We can actually come up with the safety evaluation by planning, assuming this agent is there, for instance, and seeing if that's going to cause a safety violation or not. But the problem with that whole process is that it's just too slow to run in real time. So here we are trying to use a neural network to quickly assess, given some perception uncertainty and given some plan, is it going to cause a failure or not, or is it likely to cause a failure or not?
I have one more question.
Yes.
So if we have this predicted uncertainty, is it more typical to do kind of many rollouts that kind of sample from the predicted distributions, or do you try to reason in like a Bayesian way or some kind of distributional system?
During the training, we are using rollouts in this particular case. I mean, I would love to do Bayesian reasoning, but the problem is that this uncertainty propagation needs to happen through prediction pipeline, which are just really complex today. So it's very, very hard to do it. Yeah, that's in general one of the challenges with modular pipelines, that one of the benefits of them is that they can really characterize the uncertainty at each output head. But propagating that uncertainty in a tractable manner is still a very, very big challenge. So we are sort of somewhat limited in planning in the uncertainty aware manner.
Okay. Thank you.
So, I mean, the exact architecture is not as important, but this is what our Spark neural network looks like. It takes as input the output of the perception monitor, so that is the predictive uncertainty, along with a bunch of information about the scene. For example, what is the agent history, autonomous car history, and what is my road graphs, where the lanes are, along with a candidate ego plan. And under the hood is this prediction of all of these agents, and then evaluate at the end of the day whether a particular plan is safe, risky, or critical. So again, a simple classifier. And the way we train this framework is actually purely in a supervised learning manner, where offline we can generate data sets by simulating different perception uncertainty and evaluating whether a plan is safe or not. Once again, that we can do offline because we have sufficient time. The only problem is that evaluation might be just too slow for doing in an online manner. So here I'm just showing the dataset generation. For instance, here, this green is again my ego vehicle. Suppose my perception monitor tells me or miss this agent. So suppose it misses this agent, and then we can evaluate whether this plan remains safe or not. So in this case, as you can imagine, whether we detect or not this agent, this plan is going to remain safe. On the other hand, if I miss an agent somewhere near the ego vehicle, the same plans is going to be unsafe. So that's how we can generate the data set. And here is a snapshot of, here's one snapshot of scenarios during the test time. So now we train that network and we are evaluating it. So this is the perceived scene, meaning this is what the autonomous car thought is the scene around it. But actually it did miss this agent. So perception monitor tells me that there might be an agent here, and it will give me some uncertainty around the position of this agent. So this framework Spark now would take this perceived scene along with the perception input and this blue plan, and will predict whether this plan is going to be safe or not. So in this case, it predicts that it's actually an unsafe plan. And then it proposes a candidate safe plan, the green in this case, which predicts the lane change in this case, that you should do lane change and keeps the system safe. Yes?
I guess for the perception thing, when you're reporting that, like, how does that work? I guess, like, or would you have that same capability when you're, like, driving an autonomous car, for instance, like, being able to tell, like, oh, what we perceive isn't actually as true as it might seem? So
the question is, how do I come up with that red thing?
Yeah.
Yeah, so I mean, there are different perception monitors in the literature. The one that we are using here is actually just doing sensor fusion. So what it is doing is taking the input from the camera and LiDAR and radar, and it's trying to look at sort of the agreement between them, which is that if an agent is detected by camera, is that also detected by LiDAR? And if any of them has a mismatch, then that's a potential, there could be a potential missing agent. And so it's just using that as a way to enumerate potential missing agents. But this is as an input to the framework. So this is not something that we developed here.
So for example, in the runway setting, I feel like when you consider something safe or unsafe, you can kind of write it down as a specification. For example, it's safe if the airplane stays in the borders of the runway or something. Now I feel like we've moved to a territory where actually instead of me saying it's safe or not, you have like a neural network that makes a judgment call on this. And I'm wondering, why can we not just, or I mean, you know, can you not just look at the different states and then just see if is within your spec or not, and why do we need to train kind of an unsafe detector?
Simply because of latency requirements. So in fact, what you're suggesting is what we are doing offline to generate data for this neural network. This whole pipeline of putting the agent at a different location affects the behavior prediction of all the other agents. That then feeds into your planner, and you're going to figure out whether that plan is safe or unsafe or not.
So it's kind of a surrogate model for the whole thing.
Exactly. So if we do that, precisely what you suggested, it takes currently, this whole pipeline can run at 10 hertz.
Okay. And then do you stress test against this guy also?
Yeah, so stress tests, not to the same extent that I proposed earlier, but we do, this is honestly very preliminary work and very recent work, so we are still developing the pieces of it. But I just wanted to present this work to highlight the difference between sort of modular testing versus end-to-end testing, and what it can enable. But here is another snapshot of the same framework where we are looking at if there was a missing agent at a different location in this scene, what will be the prediction of this framework? So red is the position of the missing agent for which this would have predicted an unsafe plan. In all cases, it will be predicting a safe plan. And in this case, it makes sense that roughly around this ego agent, but more importantly, in the forward direction of the ego agent, when there is an agent, it predicts unsafe behavior. But as I said earlier, the main reason to do this, as opposed to doing the exhaustive evaluation, is that we can run this pipeline at 42 hertz, which is the latency requirement in this particular case on a standard GPU. Okay, so let me summarize what I talked about. So probably not a news to this class, stress testing is an important validation and improvement mechanism for autonomous systems, both for sort of offline deployment of this system, or both for improving the offline design, but also for online deployment. Perhaps what we saw a little bit in the talk today is that control theory current provides a number of interesting tools for stress testing, in addition to many other stress testing tools that we have available. There are several open questions that I would love to discuss. One is, what is the advantage of system level stress testing versus component level stress testing? So we have a lot of mechanisms in machine learning, for example, adversarial robustness, which are more targeting component level testing. So given a classifier, they will tell us, like, can we classify a panda into an apple? But that's just a component level stress testing. Maybe a pink sky doesn't matter for an autonomous car. So even the component is doing really, really bad, it may not matter for the system level. So there is this question of system level versus component level that's important. The second is modular versus end-to-end testing. In a lot of cases, end-to-end spec is easy to write. It's easy to write what is the failure mode for my autonomous car, which is a collision, for example. But writing that specification of failure for each of the individual component for perception, for prediction, can be very, very hard. So there is advantage to end-to-end testing in the sense that I can write my failure criteria very neatly, but they are not interpretable, or it's very hard to use end-to-end testing for improving individual components, because what it does not tell me is where this failure came from. Was perception at fault, or was prediction at fault, or was planning at fault? So modular stress testing can actually help with that, but then writing the specs could be challenging. And finally, generalization. So the stress testing outcomes are limited by where we did the stress testing. So what environment distribution did we consider during stress testing? If we go beyond that, these results may not hold. So how to generalize or how to do stress testing in an online manner is still could be a very interesting question. I'm now happy to discuss any questions or any of these topics more. Yes.
So in the end, you were talking about that it can be useful, or it's useful to kind of break down your pipeline into many sub-steps, because, for example, one reason is that you can write down a spec for each part and then you can actually do testing on this. Now, famously, recently, Tesla claims to have developed, or at least that's what is publicly known, like kind of more like an end-to-end. We just make one deep learning stack and have it do like the end-to-end problem. And with this, I guess we probably agree that maybe you can get like half decent results, but it will be really difficult to go to like a regulator agency and be like, we're going to kind of prove to you that this is like a very robust system. I don't know, can you maybe say a little bit your thoughts on in these kind of situations where you need to work together with the regulator on the different types of systems?
Yeah, and I think like, it's one thing to go to the regulator and say like, it will work in these kind of scenarios, but more importantly, I'm thinking, suppose I'm investing money in this company, as I would think about, okay, what do I do with this result? I stress tested it, I figured out a whole bunch of failure situations. Generally, you want to improve on those, or at least mitigate them by designing some sort of fallback mechanism, right? That part becomes really challenging with end-to-end framework, because which part do you improve? Because these are not generally a single CNN, right? These are like very complex lines of codes. So it's also equally important to figure out which part was at fault when this particular failure happens, because that is going to be the way to then fix that failure. That becomes very, very challenging with end-to-end. And I don't have any better solution. This is just a problem that I've seen throughout my time, both in academia and in industry, that this is something everybody is discussing, and it's still an open area of research.
Sort of adding on to this point, have you seen cases where doing end-to-end testing dramatically cuts down the search space, in the sense of like, suppose an end-to-end system has just certain behavior where it's entirely not possible for the controller to do, whereas if you test component-wise sort of a, what's in like I think in this class calls like a natural occlusion sort of notion of like, you could just propagate all of the errors and you get giant bounds, but otherwise like end-to-end testing helps you see that.
Oh yeah, so like the what happens oftentimes is that if you do individual component level testing, the failure region that you get is much bigger. Not necessarily you should be getting it bigger, but because of the practical constraint, it gets bigger, which is that it's very hard to propagate the uncertainty from one component to the other component. If you could do that ideally, if you could do that, then they will be exactly equal. So assuming end-to-end is perfect, and what you're doing in modular world is also perfect, they should match up. Right. Because you are propagating modular errors also all the way to the downstream control level. The problem is that propagation is very challenging. So oftentimes you get a superset.
Yeah, so just go back to like, the example you brought up with like the anomaly detector. I was a bit curious about kind of like out of distribution anomaly detection. So let's say you have like the failure data set where you're kind of like giving it, like the failures from like the aircraft taxiing example. If you were to kind of like train a model to do like failure detection, how would you make it more robust to like different data sets, or at least like variations in data sets? Because it seems like if you train it on one failure data set, it's probably going to lose a lot of performance on like another.
That's true. It's so that's why I've been careful with not calling it out of distribution detection. So that's maybe is one differentiating point between anomaly detection and out of distribution detection. So I am only talking about in distribution anomalies. Out of distribution detectors is a very, very important topic and requires its own attention. So in my worldview at least, I think there are two detectors required. One is out of distribution detector. And then even within in distribution, our machine learning systems might not be perfect. So we also require in distribution anomaly detectors. And here I'm talking about the latter one. Out of distribution detection is something that we haven't handled here. And you're absolutely right. If I go to a new type of runway, it might very well be failing.
So for like those kinds of examples, just to follow up, how would you like theoretically construct an out of distribution detector?
Good question. I wonder if yeah, that's true. That was gonna be my answer. Mykel is a whole book. I don't know for one single way to do it, to be honest. But the recent advances in AI is being leveraged quite a bit for out of distribution detection. So people are combining different type of data sources. So, for example, in autonomous driving land, what is happening a lot is that for whenever there are some accidents that are happening, police needs to file a report. These reports are in language. So people are now actually using those language reports to generate those scenarios in simulation and for out-of-distribution detection. So it's a very different type of data source than what we are collecting here, but those could be helpful here. I should also come to the lecture that Sydney is giving on auto-distribution detection, and then maybe I would.
So you're saying like they were using like literally like just the text of like the reports in conjunction with like what the model is perceiving?
So they're using the text reports and using the generative models to generate the simulation scenarios then.
So given like the report, you could generate like the exact scenario that it's describing, and then
exact scenario, yeah. I mean, I'm going to put that in air quotation because from text to generation, it's still like not one-to-one mapping quite, but yes. So that's the idea. So that way you can stress test the system maybe beyond what you have envisioned here by using different data sources. So that could, Gen AI could really help in such kind of scenarios. Other questions?
So one interesting topic you touched on is that you want to like propagate uncertainty through many stages of your system, but it's like really difficult to do closed form. Also because you have like kind of typical runtime requirements, latency requirements. And so now more like from your, let's say, engineering experience, is it basically the solution that every individual component maybe outputs, let's say, a Gaussian or something like this, but in the end you just always sample from that, put each sample into the next stage, break another Gaussian sample from that, or what's kind of the most practical way to do these kind of things?
So I would say that accounting for uncertainty and propagating that is still a very underexplored area in industry. So I've seen very, very few companies doing that in my experience. The fact that my experience is still outdated by 3 years. But in terms of practical approaches, I think, something like what is done in POMDP literature I think is really, really powerful, right? Like these particle-based filters that are being used to propagate the uncertainty in that particular case, belief uncertainty, right? Those could be really interesting to explore. I honestly think that there's a very good scope for those set of problems. But in industry, they are really underexplored at the moment. Any other question? Awesome. Thank you.